Okay, so let's work through an example together. So here's the example, here's the circuit that we've been given, okay? The power supply is 120 volts at a frequency of 60 hertz. And here are our three loads that are connected in series. So we have a resistor at 10 ohms. We have a capacitor that is sized at 50 microfarads and an inductor which is sized at 40 millihenries. Okay? I've drawn the vectors, so this is where we're going to begin. Okay? I've tried to draw the inductive vectors and the capacitive vectors at about the same size. Okay, I have no idea what our numbers are going to look like. I don't know whether this is going to be a leading or lagging power factor. I don't know really what to expect at this point. Okay, so the final result will not be exactly to scale. Okay, but that's all right because we can just use it visually as a cue to get all the right numbers. Okay, so I mean, this is where we start. So I mean, at this point, I don't know whether my resultant vector is going to be here, way up here, right down here, way down here, or really low. I don't know. Okay, we're going to figure that out. Okay, so the only thing I can fill in here now, I do know the hypotenuse of the voltage vector. I know its value, but I don't want to put that in there anywhere yet because I don't know its location. Okay, so we're going to hold off on that. We know R. R is 10 ohms. So that's actually the only piece of information that immediately we can transfer over onto our triangles. R equals 10 ohms. So I can put that right there. Okay? I can't fill in XL and XC because I don't know XL and XC. I know the inductance and the capacitance, but I don't know the reactance. We're going to have to calculate for that. So I haven't given myself a lot of room. I'm going to have to erase my title. Let's give ourselves a little bit of space to put this in here. So how do I calculate XL from L? Who can remember that equation? XL equals two pi FL, which equals 2 pi times, what is our value for F? Our frequency in this circuit is 60 hertz. Multiplied by L, so L must be expressed in henries. We've been told the size of L in millihenries. So to translate from millihenries to henries, I must move the decimal place 3 times to the left. 1, 2, 3. So if the decimal place is there, our actual number that has to go in the equation is 0. And there's 1 0 there before we get to the 4. 0, 4. So there's our value. And I've already calculated that ahead of time. That means that XL equals 15.3 ohms. So XL equals 15.3 ohms. 15.3 ohms. There it is right there. Okay? Now we have to do the same for capacitance. We must calculate capacitive reactance. So XC equals, now remember capacitance is kind of exactly like inductance except the exact opposite. It's the inverse, and so it is the inverse equation. The inverse of 2 pi F, and this time we're calculating for C, which equals the inverse of 2 pi times the frequency is still 60 hertz multiplied by capacitance. And again, in the equation, this must be in its base form. So how do we get back to the base value, which is farads, from microfarads? Now we have to move the decimal place to the left 6 times. So the decimal place is there right now. 1, 2, 3, 4, 5, 6. Which means with the decimal there, we have 1, 2, 3, 4 zeros before we get to the number 5. So it is 0.1 1, 2, 3, 4 zeros, and then the number 5. And again, I've done the work ahead of time, calculated this out, and the answer is 53.05 ohms. So that goes down here in XC. 53.05 ohms. So now, tell me what our triangles are going to look like. I drew this vector and this vector roughly the same length when I drew it, because I didn't know what to expect. Now I have some numbers. 15 compared to 53. Okay, so this vector is really very short compared to a very long vector here. So when we subtract these two values and figure out what we have left, okay, it's going to be capacitance that we have left, not inductance. Capacitive reactance as opposed to inductive reactance is what's going to be left over once we subtract these two vectors. So again, not anywhere close to scale, but I'm going to draw a vector right there. I'm going to call that vector x, and x equals the difference between these two vectors. So 53.05 minus 15.3 equals 37.75. 37.75. I'll call it ohms just because I feel the need to always put units on things, because this is what we're talking about here. This doesn't really belong anywhere, okay? Don't put it on the answer sheet anywhere because it doesn't go in the table, okay? But it's very important because it is the opposite of our right angle triangle. Now I can draw my hypotenuse. So there's where Z goes in our circuit, okay? And I'm going to be able to figure out what the angle is going to be. And over here, I can draw an arrow right there and say that this is EX. So that is the total voltage dropped across all of the the reactance in our circuit, the capacitor and the inductor combined. And then I have a vector here, which is my resultant vector, which is EA. And then over here I can do the same thing. I'll call this RP, reactive power. Okay, you can call it RPX if you wish. RP kind of sums it up. Reactive power, reactive, feels a little redundant. Okay, again, like I say, there's no consistency in these labeling. In fact, many textbooks don't bother to label these particular vectors at all, so use whatever feels good for you. And that allows us to draw our final vector, which is the apparent power in our circuit. And to keep the videos from getting too long, I'm going to stop there, and in the next video we'll carry on, we'll crunch the rest of the numbers.